to the organizers for the invitation. I'm going to talk about something different, slightly different than the bulk of the workshop so far. I'll be talking about d-electron systems, and in particular heterostructures and interfacial properties of d-electron oxides. Okay, and I want to highlight the people that actually do the work. So the first half of what I'll be discussing is done by postdoc Hyunju Moon, and in the second half I'll talk about some new time-resolved measurements that were done by Serge Smolin, who's here in the audience, and on samples run by Amanda Choquette. Okay, so the common theme of everything that I'll be talking about today is that the material family is within this perovskite oxide crystal structure. So these have the general chemical formula AbO3. So I have an A site cation and I have a B site cation, and it gives me some crystal structure in a pseudocubic that looks a bit like this, right? And my B site cation is octahedrally coordinated by these oxygen ligands. And this BO6 octahedra I think of as sort of the functional building block within the perovskite crystal structure. It's these BO6 electronic states that reside near the Fermi level. So they are responsible for things like conduction. And it's also these B electrons that give rise to things like magnetism. Right? So I get this BO6 octahedra, and you'll be hearing a lot about this. And these form a corner-connected network, three-dimensional throughout the perovskite material. And these then residing on the corners, these are the A site cations. What these do is to help control the valence of the transition metal and also determine the bond environment in general, the size of the lattice. Okay? So when I move down, say, calcium, strontium, barium, I'm expanding the lattice, and that has implications on the local BOB bond angles and bond lengths. Okay, the other thing, just in general, that should be pointed out is the wide chemical flexibility of this crystal structure. So what's nice is that the perovskite can accommodate basically all these bluish purplish boxes on the B site and all these greenish elements on the A site. So I have a very wide chemical flexibility of elements that I can put into this crystal structure, and that gives me a wide range of physical properties to investigate. And what's another thing that's exciting is that we can now make very high quality heterostructures of these perovskite oxides, right? So we can grow these materials layer by layer in thin film form, and we can bring them together at interfaces. And because we have all this chemical flexibility, we can put a ferroelectric on top of a ferromagnetic material, and we can examine how these different properties come together and compete at an interface, right? And so there are a number of mechanisms. Rohit talked about this yesterday a little bit. But so at the interface, we can have new properties that arise from maybe BO-B prime exchange interactions, so there can be novel magnetic behavior at an interface. We can have charge transfer at the interface, the so-called electronic reconstructions. We can have orbital polarizations that arise at the interface that are not like that away from the interface in the bulk, so we can have interfacial orbital reconstructions. And we can also have non-bulk-like structural effects at the interface. And actually, this will be the majority of what I talk about today. So I'm just going to give two examples of interfacial phenomenon that my group has studied that I thought would be of most interest to this workshop. So in the majority of the talk, I'll be discussing these octahedral rotations and how we can realize non-bulk-like octahedral rotations in these heterostructures, and how we can use that to realize crystals that have spatially varying electronic bandwidth and spatially varying magnetic exchange interactions. And I'll talk about some of the future directions that I think that opens up. And then in the second half of the talk, well, the second, maybe third of the talk, I'll be discussing some really recent results on photoexcited interfacial charge transfer, or what we interpret to be interfacial charge transfer. I thought this was appropriate for the workshop, given all the time-resolved work, and also in the spirit of a workshop discussing unpublished results that we're still trying to make sense of. Okay, so let's focus on these octahedral rotations. So in general, this is sort of the implications of having these octahedral rotations. You can see that these oxygen atoms are displaced from the ideal face center positions. This is a unit cell doubling distortion, so this will come up when we characterize these. They double the unit cell, so they cut the reciprocal lattice in half, giving rise to half-order diffraction peaks. That'll be important. And the physical implication is that these octahedral rotations lead to these BOB bond angles that are less than 180 degrees, right? So we can have bond angles that are like 160 or 150 degrees, right? And this is not just a neat crystallographic feature. These bond angles directly couple to the electronic bandwidth. So in general, this theta is the BOB bond angle, and this D is the BO bond length. Okay, so as I crank up the magnitude of these octahedral rotations, as I reduce theta, my electronic bandwidth will go down. Okay, so my system will move from more itinerant to more localized as I crank up the magnitude of these octahedral rotations. And this is known from a lot of canonical bulk studies. So for instance, in the rare epithelates, as I move from lanthanum to praseodymium to europium, etc., I am reducing the size of the A-site cation. Okay, so I'm contracting the lattice, and that leads to larger and larger of these octahedral rotations. Okay, so as I do this isovalent substitution here on the A-site, I move the system from itinerant to more localized, from metallic to insulated. Okay, I'm not changing the electron count on the nickel. We're just changing the bond environment of this nickel 06 octahedra. Another example, and Rick showed this phase diagram as well, is in ferromagnetic ordering in the manganites. So the canonical double exchange phase of the manganites, right? As I go from lanthanum strontium to lanthanum calcium to praseodymium calcium, again, I'm doing this chemical pressure trick where we're reducing the size of the A-site cation, shrinking the lattice, that cranks up the magnitude of these octahedral rotations, and that weakens the double exchange interaction because the carriers have less electronic band. Okay? And you can see the Curie temperature drop as you do that. Again, you're not changing the manganese nominal valence. This is all just from playing with this octahedral environment. Okay? So what I hope to show is that what I hope I've convinced you is that in bulk, these rotations are important for the physical properties, electronic and properties of perovskites, but also in bulk, they're controlled by the chemistry of the system. Right? So if you want to change the octahedral rotations, you have to change the A-site cation. Now in heterostructures, what is, I think, exciting is that we now have two new knobs that we can turn to vary the magnitude of these octahedral rotations and to release non-bulk-like atomic structures. So the first thing that we can use is epitaxial strain, where I take my film and I deposit it on the substrate. That substrate has some different lattice parameters, and so the in-plane lattice of the film that I'm growing has to either expand or contract, go under tensile or compressive strain to accommodate this bonding with the substrate, right? And then that compressive or tensile strain, the octahedra have to accommodate that, and so that'll perturb the rotations of distortions. And the other mechanism, this is what I'll talk mostly about today, is this idea of interfacial coupling, where I take one material maybe that doesn't have rotations, another material that does have rotations, I coherently join them together at an interface. I need to maintain this corner-connected network, and so at that interfacial region, I'll have some octahedral behavior that's not like what's found in A, but not like what's found in B. So it's sort of like an interfacial proximity effect. Okay, so quickly, just one slide on strain, and also to introduce this idea of how we measure these in thin films. In bulk, people do powder diffraction, but in films, we don't have that. We can't do that on a single crystal 10 nanometer thick film, right? So we have developed this technique using synchrotron diffraction, where we measure these half-order diffraction peaks that come from this unit cell doubling of the octahedral rotations. And by analyzing them, we can determine, because in these materials, in some of these materials, these rhombohedral perovskites, the only unit cell doubling distortion is these octahedral rotations. So the only atoms contributing to these half-order peaks are the oxygens. By analyzing the intensity of these peaks, we can get at the oxygen positions, right? And so we've done this, for instance, in lanthanum nickelate, and we've looked at how, when you strain the material, you grow it under compressive or tensile strain, how these octahedral rotations accommodate that strain. And it kind of does exactly what you would think. If you stretch it, it unrotates about this axis and has to rotate more about the other axis. But it's nice to have a technique and to actually experimentally demonstrate what happens under strain. Okay, but as I mentioned, I really want to talk about this interfacial coupling. And so over the last few years, there have been a number of really nice structural studies, transmission electron microscopy, and advanced surface diffraction techniques like COBRA that have allowed people to map out these octahedral rotations across hetero interfaces. Right? And these have shown that as you move from one material to the other, you'll have this region, as I mentioned earlier, where the rotations go from A to B, and you get something in between the two materials. And a variety of these studies have found that this length scale for interfacial coupling is on the order of 2 to 8 unit cells, depending on the adjoined materials, right? Depending on the stiffness of all these bonds. All right, so we've established that this phenomenon exists in these heterostructures. How can we actually use it? So that's what I'm going to show over the next couple slides. And again, I'm going to be playing with this length scale, right? So I combine A and B. I have some length scale over which the magnitude of these rotations are varying between A to B, right? And so if we play games with that length scale, I think we can get at new physics, right? And so, as I mentioned, we can make these heterostructures, we can grow these materials layer by layer. So we can make superlattices where we have A, B, A, B, A, B, A, B, right? And we can control the number of layers within each of those blocks, right? So as we make, say that we make a large period superlattices, we have a lot of A, a lot of B, a lot of A, a lot of B. Or to put it another way, the distance between these interfaces is larger than this length scale for octahedral coupling. Then what we would have is a very modulated octahedral distortions as we move along the growth axis, right? Or what we can do is we can push these interfaces, we can make a short period superlattice where we push these interfaces closer together than that length scale for octahedral coupling. And now what we would expect is to get a structure that's much more uniform along the growth direction, right? So we can go from something that's highly modulated to something that is much more uniform by changing the period of this superlattice, right? And so then as a result, we should have our electronic and magnetic properties that are much more uniform and that are modulated in the long period structure. Okay, so that's what we're setting out. That's the physical idea I'm going to be setting out to show. All right. Now, as I mentioned earlier, though, we have all these other degrees of freedom. We can have charge transfer, we can have orbital effects, and I really want to get at this one variable, which are the magnitude, which are these octahedral rotations, right? So we need to control for that other stuff. And to do that, to make sure that we don't have any charge transfer, what we're going to look at are isovalent superlattices, okay? So we're going to look at two magnetites, lanthanum, strontium, magnetite. This is the 30% strontium doping. This is the canonical double exchange CMR sort of material. This is what it looks like in bulk. Lanthanum, strontium, magnetite, LSMO has a Curie temperature of around 350 Kelvin, and it has these bond angles of 164 degrees. The other material that we're going to use is europium strontium magnetite. Europium is smaller than lanthanum. The lattice contracts, it cranks up the rotations, and you have a bond angles that are 157 degrees. And as a result, the Curie temperature goes down to 80 Kelvin. Right? But the key here is that both of these are the same doping, and so the nominal manganese valence is the same. So when I join them together, no charge is going to move from one material to the other because they're isoelectronic. Okay, so as I mentioned, our group, we do oxide MBE. Here's a picture. It's a relatively small chamber, but we can grow it, very nice quality material. So here's just a STEM image showing that we can make nice abrupt interfaces. An AFM image showing that our surfaces are smooth with one unit cell step terraces. And here is an example of this kind of control that we have in depositing the materials. We can make sort of metastable cation orderings where we have 2 unit cells of, in this case, these are ferrites. We can deposit 1 unit cell of A-site cations and then 2. And we actually see those in the X-ray. So we have this nominal unit cell control of our growth. Okay, so these are the superlattices. Again, LSMO, ESMO. Here's a STEM image that was taken by Albina Borsovich at Oak Ridge. And this is showing, and what we're going to look at are symmetric superlattices. So where the number of LSMO layers is the same as ESMO layers. Okay? And this is Z contrast, so there's not a lot of contrast between lanthanum and europium, but there's a little bit. And you can see these stripes here, lanthanum, 11 unit cells of lanthanum, 11 of europium, strontium magnetite, and this repeats a couple times out. And you can see that we have nice, well-defined interfaces. If you would rather see this in reciprocal space, here's the diffraction data. These are L scans of the 3, 3, 6, 6, and 11, 11 superlattice. In simulations, just assuming everything is absolutely perfect with perfect interfaces, and it's kind of remarkable how well the simulations actually match the data. So I hope to convince you that we have nice superlattices, that these aren't just random outliers. All right, now moving on. I mentioned those half-order diffraction peaks. Okay, so again, these are these half-order diffraction peaks that arise from the unit cell doubling of these octahedral rotations. So they're sort of like satellite peaks in some sense. And this idea that we have these modulation of the octahedral rotations. So anytime you have a periodic modulation in a crystal structure, that will also give rise to a diffraction peak, right? And so we in fact see that, and these are the 3 different superlattices again, we see a satellite peak off of the half-order diffraction peak, right? So we see, and that tells us that we have a modulation of this unit cell doubling distortion, which are the octahedral rotations, right? And the periodicity that we get from this satellite peak matches the periodicity of the superlattice. Okay? So the octahedral rotations are modulating about the C-axis with the period exactly what we would expect that of the superlattice. There's a bit more information in here that I can talk about if someone's interested, but that's the main takeaway. We have this modulation. Okay, so let's look at what happens to the physical properties. We'll start with just very basic magnetization, because this is relatively easy to measure. So here's magnetization versus temperature. And you can see these two kind of kinks in the data, suggesting two transitions. This really pops out when you do DMDT. You see these two local maxima. One occurring, and again, this is the 1111 superlattice. So we're starting with the interfaces as far away from each other, so we would expect the most modulated structure. All right, and so here we see a Curie temperature around 320 Kelvin and one around 80 Kelvin. These match up very well with the bulk, lanthanum, strontium manganite, and europium strontium manganite. So this suggests that the LSMO layers are acting like LSMO, the ESMO layers are acting like ESMO. Right? We push them far away enough apart that whatever this interfacial perturbation is, it's not dominating the physics. Okay, that's what it looks like. We can actually prove it with polarized neutron reflectivity, where we come in with polarized neutrons that are aligned parallel to the magnetization in the sample and anti-parallel to the magnetization in the sample. And from that, we can get out the magnetic scattering potential. And this gives us a depth profile of where the magnetization is within the sample. So this is a commonly used technique for thin films and heterostructures of magnetic materials. And these were done with Mike Fitzsimmons, who's now at Oak Ridge. Okay, so we get the data. You get two different curves, one for parallel and one for anti-parallel reflectivity. We can fit them and we can extract from the magnetic depth profile throughout the superlattice, right? And then what do we see? We look at 100 Kelvin. We see no magnetization in the ESMO layer and magnetization in the LSMO layer. So sort of a fancy experiment to tell us exactly what we would have expected to happen, but now we have proof. All right, so moving on then, let's start to push the interfaces closer and closer together. So we'll make a 6-6 superlattice. And what we can see right away is that the LSMO Curie temperature has come down significantly, right, to about 240 Kelvin. But kind of interestingly, the ESMO layer seems to have gone up to 100 Kelvin. Right? And typically when you make magnetic oxides, as you make them thinner, the Curie temperature always goes down from finite size effects. Here we made the ESMO layer thinner and the Curie temperature has gone up. Well, this is exactly what we would expect. Right? The LSMO structurally is becoming more like the ESMO, and the ESMO structurally is becoming more like the LSMO. So the Curie temperatures are going to start to come together. And then by the time we go to the 3-3, we see this basically one distinct Curie temperature, which is in between that of the LSMO and ESMO. Right? So this suggests that we move from this highly modulated atomic structure with modulated magnetic properties to a much more uniform structure. Right? And you can say, wow, that's great, you just made a random alloy. But of course, we can make a random alloy, right? We can just throw all the atoms together into the film, measure the magnetization, and the magnetization of the random alloy, the Curie temperature is significantly lower than that of the superlattice, right? So by making the superlattice, we remove a lot of this cation disorder, and that also helps the exchange interaction and brings up the Curie temperature. All right, so why do I think this is interesting? Well, first, there's been a lot of work in our field looking at heterovalent superlattices. So for instance, we take lanthanum manganite, strontium manganite, we have a D4 and D3, we get some charge transfer at that interface. And so this is kind of like delta doping has been done in the semiconductors. We can insert certain layers that have a different valence, some of that charge leaks out, and that locally confines some property, right? What we've done is the structural equivalent to that. No charge is getting transferred between the layers, but sort of structure is getting transferred between the layers. These octahedral rotations are coming out of one layer and going into the other, right? So we can do a lot of the tricks that can be done with delta doping, but now do it structurally. Well, is that actually true? Can we push this to the limit of delta doping where we just put in a couple unit cells? Right? So here's some recent work, unpublished stuff, where we're looking at, again, isovalent manganite superlattices, 2 unit cells of this lanthanum strontium inside 20 unit cells of lanthanum calcium. Again, LSMO is going to have less rotations, so it should have larger electronic bandwidth, larger ferromagnetic exchange. All right, so these are, again, STEM images by the Oak Ridge folks. And here's the STEM image of the superlattice. And locally, they can go in bright field imaging and look at the projection of the oxygen positions. And they see that locally within this LSMO, they get this reduction in the magnitude of these rotations, just like what we would expect. And again, we can then go to polarized neutron reflectivity, and here's showing the fits to the spin asymmetry. And we can see that we get this enhanced magnetization inside the LSMO layers compared to the LCMO matrix. Okay? So this shows that we can use this sort of structural delta doping technique to spatially confine magnetism within a coherent 3D crystal. Right? And so normally if we want to take a perovskite and we want to study how the magnetic properties are in reduced dimensions, we need to just make a very thin film, right? Maybe just a couple unit cells. But that's a very different beast than the bulk because we have all these dangling bonds at the surface. we've got interfacial bonds. But here, within this technique, where we put a material with reduced rotations inside a matrix that has large rotations, we maintain that MnO6 3D network, right? Where we just get this thin region where we have enhanced itinerancy and enhanced magnetic properties. All right. The other thing that one could point out is that if we have control, we can realize these spatially varying, and we can dial in these modulations of the octahedral rotations. There's other implications for that as well. So, for instance, the Dilichinsky-Maria interaction in perovskites comes from these octahedral rotations, right? And that leads to some spin canting. So there's a lot of interest in spin textures right now, and how they couple to magnetotransport properties, for instance. And we can imagine using these spatially modulated rotations to realize new routes to achieve, say, modulated spin canting structures. This is, of course, not drawn to scale. We can't count the spins that much by these rotations, but it gives you the general idea. And also, these hybridization of the BO bond is a key factor of that is the rotations. So we can also think about making superstructures of hybridization through the material, again, by changing locally how these rotations work. Okay, so that's the first part on how we can use structure to achieve sort of non-bulk-like properties in crystals. All right, what I want to touch on here in the last couple minutes is this idea of using photo-excited interfacial charge transfer. And that, as Rick pointed out so nicely, one of the really exciting things in that field is realizing new phases that don't exist in the material, kicking the material into a metastable phase. And so I think maybe this is an opportunity as well. This might be a strategy we can employ to do that. And as I mentioned in the very beginning, these are unpublished results, surges here. We're really happy to get any feedback we can. We're still trying to make sense of what this means. There's more data that I'm not going to show here. Okay, so I mentioned at the beginning, one theme that's been pursued a lot in oxide interfaces is this idea of charge transfer at an interface, or an electronic reconstruction, where the unit cells at the interface have different electronic properties than they do away from the interface, because that interface has perturbed the electronic structure. So there's many examples of this LAOSTO, titanate superlattices, magnetite superlattices I just alluded to. Here's an example that I think is a relatively clean example. Lanthanum magnetite, lanthanum nickelite. Away from the interface, this manganese and this nickel is nominally 3+, right? But at the interface, what happens is that there's this charge transfer. The manganite gives an electron over to the nickel, and at that interface, you get nickel 2+ and manganese 4+. And this nickel 2+ then is ferromagnetically coupled at the interface. You see some XMTD signal on the nickel. It looks like 2+. And so you get this emergence of the exchange bias at the interface and ferromagnetism on the nickel because you have this charge transfer. Away from the interface, it's just paramagnetic lanthanum nickelite. All right. And then also we've heard a lot at this workshop about how exciting of a field this is using ultrafast spectroscopy and other techniques to realize transient phases and correlated oxides. So Rohit has done a lot of work on this, for instance, recombination kinetics and looking at multiferroics. There's this beautiful example of this terahertz induced MIT and VO2 from Keith and Rick. And also, there's been work on photon pumping to induce metal insulator transitions in nucleus. This is all really exciting work. These studies are all basically done on one material, though, a thin film of a single material. So we combine these two ideas, charge transfer and transient phases, into one, right? So what happens if we take two perovskites together and we photoexcite carriers at that interface? Right? Again, this is work that Serge is doing with his advisor, Jason Baxter. The idea is that, maybe I come in, I put two semiconductors together, I hit it, I excite the carrier, some of the carriers move over into the other material, and now, as Rick mentioned, we could excite a lot of carriers in these high fluence regimes. Right? We might be able to move across phase boundaries here if we add 1/10 of an electron per unit cell or something like that, and realize and stabilize a new phase at that interface that can be sort of metastable. So can we stabilize near interfacial transient phases through charge transfer? All right, so we're just dipping our toes into this. We want to start with two relatively simple systems that have been characterized. We're going to take lanthanum ferrite and lanthanum magnetite. Lanthanum ferrite is a semiconductor with a gap of about 2.4 eV. It's a G-type antiferromagnet with a very high Yale temperature. It has a nominal D5 iron 3 plus configuration. Here's what the optical absorption looks like. You have this band gap here around 2.4 eV, and then there's this second transition that kicks in here around 3.5 eV. You'll see these show up in the transient absorption data. Lanthanum magnetite is a narrower gap material, about 1.1 eV. Right? In our ellipsometry data, we can't get down that low, so that's the literature value that's reported. It's an A-type antiferromagnet with a Néel temperature of 140 Kelvin. It also has this static Jahn-Teller distortion. It has this famous orbital ordering in it as well. And it's nominally 3D4 manganese 3 plus. Okay? And again, there's this higher energy transition, about 3 eV. This will be important in looking at the transient absorption data. So we grow these materials by MBE. Here's a picture of the interface. This is STEM, Z contrast. This is lanthanum and lanthanum, so you really don't see any interface because the manganese and the iron aren't really contributing to the contrast. But you can do STEM imaging across that interface, and you can see this relatively abrupt interface as you go from lanthanum ferrite to lanthanum manganite. With the STEM yields, you can also look at how the valence state changes as you move towards the interface, right? And so the important takeaway here is that the manganite stays 3 plus as you move to the interface, and the ferrite stays 3 plus as you move to the interface. So in the non-perturbed state, you put the interfaces together, and both there's not significant charge transfer statically. The materials stay 3 plus. All right, here's what the transient absorption spectra look like. This is all just measured at room temperature. All right, so this is lanthanum ferrite excited at 4 eV, so above the gap. And this is just a plain film of LFO, so this is a control. All right, so what you see is that there's 2 negative transients that occur right around those optical transitions. And we also have this positive feature here around 3 eV. And then here's the time dependence of them. You excite, they last, and then they decay over. Here's the lanthanum magnetite. There was that transition at 3 eV. Again, we get a negative transient around 3 eV. This is the same energy that we get this positive transient in LFO, so that's going to be important. And down here, these lower energies, 2.5 eV, we see sort of a positive transient. Okay? So that's what the two materials look like when they're not attached to each other. Let's attach them together in this, say, 20 nanometer bilayer, and what do we get? Okay? So this is what the spectrum looks like. So at short times, 2 picoseconds, it looks very much like lanthanum magnetite. Okay? You have this positive intensity here, you get this negative delta A over here, right? So it looks a bit like this. But what I find really remarkable is that as we go out to larger time scales, 100 and 1,000 picoseconds, you look at the spectra at 1,000 picoseconds, it looks just like LFO. And the important thing that I forgot to mention, this excitation, okay, so this spectra here is excited at 1.5 eV. This spectra here is also excited at 1.5 eV. So this is excited below the band gap of LFO. Okay? So in this data, we're not directly exciting any pairs within the LFO. Okay? So we're exciting pairs within the LMO. Okay? And then over time, we're just probing the spectra, right? And then over time, the spectra starts to look like LFO. Okay? And so to us, this suggests that maybe there's some charge transfer occurring on the order of 100 picoseconds. So a scenario that can fit this data is that, well, we're coming in with light, we're exciting within the lanthanum magnetite, we excite this electron, it has this smaller gap, the electron gets stuck here. But if these valence bands are lined up correctly, this hole can migrate over to the LFO, and then that can lead to a bleaching feature in the lanthanum ferrite, right? So it takes on the order of maybe 100 picoseconds for this hole to migrate over, because these mobilities and perovskites are relatively low. Really, to nail this down, we need measurements of band alignments, right? I can draw this in PowerPoint, but is it the real actual band alignments? And so XPS measurements are underway. But I think that I'm excited about it because I think it points to this possible ability to dump a lot of charge into a material via whatever it's bonded to, right? So there's been a lot of work on gating of perovskites as a way to change charge concentrations to move across phases. This might be an alternative approach whereby we can realize even larger amounts of non-equilibrium charge dumped into a material. All right, so with that, I want to summarize. Again, I hope to show you that we can control these octahedral rotations, and that's a neat way to tune properties in oxide heterostructures, and also that we're dipping our toes in this photo-excited charge transfer at oxide interfaces, and we think this might be an exciting area for future exploration. Serge and I are around for the rest of the workshop, and we'd be happy to talk to anybody about helping us make sense of this second part of the talk. So thank you, and again, thank the organizers, and I'd be happy to take questions.
questions?
So all my questions I have was 100 picoseconds because of mobility slow. So can you also tell how this relaxes back to equilibrium, this nanosecond time scales, or how this has to relax problems under momentum? So, do you know this?
Yeah, that's a great question. So that's the setup that is at Drexel. You know, it only measures out to 3 nanoseconds, and then there's what's the time rate on the rep?
It's at 1 kilohertz.
1 kilohertz. So we're missing a whole big chunk of time, right? That we'd really like to know the dynamics in there after nanoseconds, kind of up to microseconds, to see how long. In principle, this should be a relatively longer-lived state because we've moved the hole into the other material. We've separated the hole in the electron. It'd be really nice to have direct proof of that.
So, but after nanosecond, there's still a big
Yeah, after, I mean, so this is showing it 3 nanoseconds, right? At 3 nanoseconds, the spectra looks quite like LFO. Even this feature is even grown as you go from 3 picoseconds to 3 nanoseconds. Yeah, and so what you showed yesterday with the time resolved XAS, it would be very nice to actually go onto the manganese and iron edge and see if you're actually seeing charge transfer between them over these time scales. Yeah, that would be nice. We've done some other measurements in the cross data at lower temperatures. This is quite new data, so I think that makes sense as a sort of a next area to explore.
Just go back to, I guess, one slide.
Yeah.
So just curious if, just as a check, if you took alpha, pure alpha, you did 1.5 on that. I just wonder if there's speeds of 90 photons.
Right. You've done that, right?
We did that, there's no signal.
That was one of my first questions too.
Definitely look at charge transfer.
Yeah.
Can I ask you a naive question? If there's charge transfer, why do you expect to get the same sort of spectrum as you get for pure LFO? Would you be having some kind of basically a different material, I think it is?
Yeah, that's a good question. You know, does the band structure change as you dump this extra hole into it?
Right.
Yeah, it doesn't appear to be what we see. I mean, this looks like just the normal LFO. So it's interesting to think about. Because as I say, if we dump all this charge into a material, it's not like, you know, exactly, it's not the same material. Exactly.
You guys consider the penetration depth of the light structure if you're moving across, from 1.5 eV to 40 eV, if your LFO band has 2.4 eV, and on one side you're about light going all the way into the LFO there, on the other side of the cipher, you have this significant portion. The LFO layer that can kind of hold up the cipher on your seat, the available on top.
Yeah, that's a good point. And I didn't show, but we have these bilayers. So this is, say, 50 unit cells and 50 unit cells. We have some systematic film. You know, we have got 7 unit cells LFO, 3 unit cells of LFO, 11. So we have a systematic series to allow us to control for those sort of things. And we see these features. You know, the intensities change because you have less volume of material.
Okay, great. Let's thank the speaker again.